I'd like to determine the hybridization and structure or shape for SCF4. So here's the issue. You can see we have 4 bonds. So with 4 bonds, is it tetrahedral? Is it going to be seesaw? Because that would have 4 bonds. Or is it going to be square planar, which also has 4 bonds? So we need to figure out which it's going to be. So if I take SCF4, selenium has 6 electrons. Fluoride has 7 electrons. So that's going to be a total of 34 electrons. That's the first thing we want to do, is just determine the number of electrons. And then I'm going to make the Lewis structure. And I'm going to do this real quick. Always got to do Lewis structure, because that tells us the number of electron groups. So if we do this, that's only 32 electrons. So I'm going to I need 2 more electrons, and I'm going to put those as a lone pair. Okay? Because that's going to be my 34 electrons. So now I've just determined that I have 5 electron groups. So I need 5 orbitals. Okay? So 5 orbitals is going to be sp3, that's only 4d. So that's how many that's going to be my hybridization. Well, tetrahedral is sp3, so that's out. Square planar, believe it, let's draw tetrahedral real quick. There's no lone pairs. Seesaw kind of looks like this. That comes from the 5 groups. Square planar originally comes from octahedral, and you have your lone pairs on top and bottom. So it's not going to be square planar, because that requires sp3d2, or 6 groups. So the answer is going to be seesaw, which comes from trigonal bipyramidal. So let's work with this a little bit. So I'm going to have selenium right here in the middle, and I'm going to have 5 groups. So normally your 5 groups would be trigonal bipyramidal. That's the electron shape. Okay, and I have my electrons coming out and going back. All right, you know one of these is going to be the lone pair. So that's going to be our problem. Which is the lone pair? Is it axial? Okay, so here's an axial. Is that where the lone pair is? Or is it equatorial? Is that where the lone pair is? One of the equatorial. Okay? So that's the question. And it all has to do with electron repulsion. The electrons want to be as far away, especially from a lone pair. Okay, so let's take a look. What if we drew this and we put the lone pair as axial? Is that going to be right? So here are my fluorides. And maybe you just look at this and go, it just doesn't seem right, because it's not. And when you look at the angle between lone pair and 4 bonding pairs, those 4 bonding pairs that you see, that's a 90-degree angle. Okay, so here's the other way. That's if we took off this bond right up here and made it a lone pair, which is what we need. We need a lone pair. Or is it this way, where we have selenium in the middle, my two fluorides. I'm going to put the lone pair as equatorial. Okay, and I'm going to put my bond going back, my bond coming out. Okay, so I removed this bond right here instead. I removed the equatorial bond. Now what you can see is only two lone pair to bonding pair angles are around 90 degrees. Okay, so right here and right here. And the two others are greater than 120. So this is going to be the correct, because the distance between the bonding pair and the lone pairs, there's fewer 90-degree angles and they're farther apart. And so this shape is seesaw. So determine the number of electron groups first with the Lewis structure. That tells you how many orbitals you need. So in this case, we need 5. That's sp3d. So that's going to rule out most of our shapes. So then the general electron shape is going to be this one right here, which 5 groups, that's trigonal bipyramidal. The problem then is that you've got to decide, do we remove the axial pair and put it with a electron pair, the lone pair, up here at the top, or is it going to be here on the equatorial? And the answer is the lone pair is going to go equatorial, not axial, because it allows you to have the angle between this lone pair and your bonding pairs is going to be the greatest distance.